Thank you for Professor Holland. It's great to be back at Trinity. And not only at Trinity, but in the science area of Trinity. And not only that, but to have in the audience the girl who sat next to me as freshman biology. And again, I will not say how many years ago that was. And it is an honor to be here as a guest of Professor Holland. Professor Holland and I share an interest in zoology, and within that, specializing in parasites and parasitic diseases. And Professor Holland also writes the books that help the rest of us to make sense of the oceans of information that these days engulf us. So I'm very happy to be here under her, at her invitation. My own interest in parasites has been varied, but mostly been focused on the treatment of parasitic diseases. And it's only in recent years that I realized that that actually goes back in a way to my early teenage years, when I was growing up in this town in County Donegal. And here you see I grew up in that street, and that's a family shop, a family cows, family dogs, so on. I'm also very happy to have in the audience the son of the revered minister of that church on the skyline there, and also another man who grew up near Milton. I'm glad to have both of them. So when I was growing up here, I also was attending a boarding school in Belfast. And on that occasion, we were taken once to an agricultural show somewhere near there. And I remember nothing about it except one thing. And that is coming away with a little leaflet, a pamphlet advertising a drug for the control of liver fluke, of cattle and sheep. And there you see the liver fluke. I even remember the drug that was being advertised, hexachloroethane. And oddly enough, decades later, I had a chance to set up my own liver fluke program, from which a new drug emerged, which also had its advertising pamphlets and so on. So in a sense, there was a sort of full circle there, although I certainly was not aware of that at the time. So I want to leap forward now for many years after my Trinity days, after grad school in the United States, after I joined the Merck Institute for Therapeutic Research, and had been there a good many years. So a lot of time is passing before what I will talk about next. And I want to focus on the search that will lead to the drug that Professor Holland mentioned. And this was a search at the time for a new anthelmintic, that is a new drug against parasitic helminths, parasitic worms. And in this talk, when I say we, I'm talking about the research staff of Merck and Company, not any individual, and I'll mention that later on. So we had the benefit, after I joined Merck and in the intervening years, of having introduced thiabendazole, which was the first of the benzimidazole anthelmintics, which were the first modern broad-spectrum anthelmintics. But as with other drugs, it had suffered from the two great inevitabilities of competition and drug resistance. And other companies and ourselves were introducing various drugs that were a little bit better, a little safer, a little more potent, or whatever. But we decided we didn't want to do that anymore, that it was time for something completely different. And we realized that the way to look for something completely different in terms of a chemical compound was to turn to microorganisms, to microbes. And the reason for doing that is that microorganisms can make things that human chemists cannot even dream of. And the bacteriologists had known this, of course, ever since penicillin, for example, that microorganisms can make all kinds of weird and wonderful chemical structures. But parasitologists were not using it for various reasons, all of them really methodological reasons. And so the first thing we had to do was develop a new assay method. And this method, in a way, it will seem almost anti-scientific in its crudity, but what we did was collect a lot of microorganisms from various parts of the world So we could take advantage of the fact that the ground, the soil all around us, is absolutely loaded with microorganisms of all kinds, some known to science, some totally unknown. So we collected these from all over, and we allowed them to grow in a nutrient liquid until you got a real good fermentation going. And then we took that fermented broth and dried it and added it to the diet of mice that we had infected with worms. So the mice were eating their regular diet, but were also eating a lot of microorganisms, which of course we do every day ourselves without knowing it, just as the mice didn't know it. And then we checked the mice to see if they still had worms after a certain number of days. The source of our microorganisms was soil around the world, and I show the slide just to mention that we were getting them from all over the world, and the one that happened to be paid dirt in sort of a literal sense was a culture we got from the Kitasato Institute in Japan, because we had previously set up a formal arrangement with the Kitasato Institute, now Kitasato University, so they would send us microorganisms that they had isolated from soil, but that they were not really interested in because they didn't really have antibacterial activity, but that looked different. There was something special about them. They weren't just a run-of-the-mill. And of course, they didn't know what they were, and we didn't know what we were when they received them. And there was one particular batch that sat on our shelves for over a year, and then we finally decided to test that batch in our new assay system. And this is what we got. Now, I should say that one of the problems with this assay is that we had no idea what was in this stuff, this gunk, this fermentation. It would be all kinds of stuff that various microorganisms, bacteria and fungi might have produced or might not. If there was something there, it was probably there in extremely small amounts, trace amounts. And then we were diluting it further by mixing it in with the feed of the mice, and we're diluting it even further still because it's been distributed in the body of the mice that would eat them. So it's really very unlikely that you'd find anything this way, but we did, and this was it. And of course, we didn't know what it was, and it had not been named. It is a new species of bacterium. It is a filamentous bacterium, so there are zillions and zillions of bacteria in that patch that looks like a mold they're growing on an agar surface. And it was extremely potent. But when you think about it, we wouldn't have discovered it had it not been extremely potent. That was the good part of it. And if you take some of the stuff that we got, the crude stuff, and refined it just a little bit so that you knew you had got the part that contained antiparasitic activity and that the rest was rubbish. But even that sort of still very crude stuff, if you added it to the diet of mice, it would get rid of their worms when put in the diet at a concentration of 0.000%. I mean, this was fantastic. No, that sort of potency had never been seen before. And you might think, well, that must have been very exciting. We must have been excited. But no, because in this business, you realize when you discover a compound against some disease that you're working on, it is intrinsically exciting for the moment. But you also know that the chances are overwhelmingly strong that it will fall apart next week. It'll be too toxic, too unstable, too stinky, too anything. So the chances of surviving to the market or to the clinic is very small. But as time went by, it overcame all these various obstacles and continued to look very good. So we continued to pursue it, and our microbiologist described it as a new species, Streptomyces avermitilis, later also named Ivermectin. So this stuff that we got out that was so active against worms, we called it Ivermectin. This was actually a word I made up. It was trimmed a little bit by my boss. But the idea was that the A and the verm, the A would mean no or not, and the verm would mean worms, no worms. And then the ectin part will come in later, as I showed, have to do with ectoparasites, parasites that live on the body rather than in the body. And there was a huge amount of chemistry being done right away by isolation chemists and analytical chemists. And they finally discovered what it was. But before they discovered exactly what it was, they had these various constituents. It was made up of 8 very closely related compounds. And they were given these code names. There was A1, B1, and so on. And this happens to be B1A. And I'll show you the structure in a moment. But our chemist friends certainly agreed with us in biology that microorganisms could make a compound that a human chemist could never think of. But the chemists seemed to believe that only a chemist can make it right. And so, of course, they were tinkering with this from the beginning, doing everything they could to change it. But more than that, they focused very carefully on the data we were giving them and the structures that they had identified. And they realized that if you took that antiparasitic data and compared it to the structure, that those 8 components were not all equally useful or active. One was particularly active, which is this one, and another one was not quite so active, but was a bit safer. So the chemist tried to tinker with the molecule to make a sort of hybrid of these two and get the best of both worlds, and that's exactly what they did. So on the upper left, you see this is the one that was most active, Ivermectin B1. I'm not going to discuss the chemistry, partly because there isn't time, but mostly because I don't actually know any chemistry. But my chemist friends have told me that this is a macrocyclic lactone, the big central part hanging down. It has various bells and whistles. And coming off on the upper left there's a sort of long tail composed of 2 sugars, unnatural sugars. And if you remove one of them, it's still a pretty active compound against parasites. If you remove both of them, you lose antiparasitic activity. So you'd be tempted to think that those 2 sugars were needed for antiparasitic activity. However, if you remove those 2 sugars and the hydroxy group at carbon 13, you restore antiparasitic activity. And there is, in fact, a related series of compounds called milbemycins that have just that structure, and they're also very strong antiparasitic agents. But what the chemists did then is on your lower right, and of course you will all have spotted the difference immediately, but just in case you haven't, so I can see it in front of me, but I can't point to it, I guess. You will see up in the upper right-hand corner there is the bond between the 22 and 23 carbon atoms. There's a double bond. So what they did was they hydrogenated this compound, they added hydrogen, and made this saturated bond, single bond, which you see down below. So this is a single bond at 22-23, and this is 22-23 dihydroavermectin. So we had avermectin B1 after hydrogenation. It was 22-23 dihydroavermectin B1A, and because it was a dihydro, the chemists thought, well, this is a natural, we'll call it not avermectin, but ivermectin. But in a big corporation, there are people looking out for all kinds of things, and somebody pointed out that in some important language, the word hyver means testicle. So, as a result, we have not ivermectin, but ivermectin. And ivermectin stuck. So what was so special about it? Well, I've already mentioned its chemical structure was unique. I mean, this was a structure that had not been seen by humans previously. Its mode of action was also different. Of course, that's very important when you're dealing with populations that are resistant to one type of drug. You don't want the mode of action to be too similar in case it's resistant to that also. Again, I'm not going to say much about it, but in this case, well, it paralyzes worms rather than killing them, and it does that by hyperpolarizing neurons, and it does that by binding to receptors on the glutamate-gated channel, ion channels. And it's a little tiny bit of protein that seems to have evolved to be an antiparasitic agent against worms, which, I suppose it doesn't happen that way, but nobody knows why this particular just subunit of that receptor is what ivermectin works on. And it paralyzes, especially in many kinds of worms, it paralyzes the pharynx, so the worms can't eat, and so they die. I mentioned also the potency, and I'll mention that briefly again. Potency was much greater than before. Breadth of spectrum I'll mention in a moment. I have a reminder here down at the bottom to mention teamwork. Now, this has really become a cliche for people to say, well, it was really the team and so on, and of course that's right, and it's particularly important in this case, and it becomes more important as time goes on. And nowadays there are very few Gregor Mendels toiling alone in the silence of a monastery garden. I mean, it's a very rare thing for that to happen. In fact, you have these, in our case, not just a team, but a team of teams. So I just want to emphasize that aspect. Now, just as an example of its activity, its spectrum against worms, it was active against many, just dozens and dozens of species of nematode or roundworm. And the one up on the upper left there is a common dog roundworm. It happens to be one of Professor Holland's favorite people, subject of one of her books. And it's big, inches long, and down in the lower right is the one, in fact, that we had in the mice. So it was against this worm, and you see it through the small intestine of mice. If you just look at it under a dissecting microscope, you can see the worms inside, and you can also see if they're gone, but we had other means also, of course, of checking up whether or not the worms had gone. Potency, you might think, is of not practical importance, but it does allow you to make a much greater range of different formulations if you have a very potent drug. And also, the potency against any particular parasite is not what counts in veterinary medicine and animal health. It's the potency against many parasites. And in cattle, for example, there are about 24 parasites. And in the case of ivermectin, you have about 20 of them are roundworms, and 3 or 4 are ectoparasites, insects and acarines. So you have this huge spectrum of worms, and if you're going to be competitive, you have to have claims, approved claims of all of them. So an enormous amount of work goes into this. But you can see here that the dosage over time, from when we introduced thiabendazole at 44 milligrams per kilogram, successive drugs were more potent than the ivermectin, just as a fraction of a milligram per kilogram. The other thing about the spectrum I've mentioned a couple of times has to do with ectoparasites. And this one is sort of close to serendipity. I resist a fairly common attempt to describe the whole discovery as serendipity. This one also I would not even acknowledge as serendipity in the true Walpolean sense, but it comes close because in our animal colony there was a rabbit with this ear mite infection. The whole inner surface of the ear completely encrusted because of this mite infection. And my colleague, Dr. John Egerton, who did a great amount of this work, and my other colleague, Dr. Dan Ostland, also involved in the assay, which incidentally involved only 1 mouse instead of a group of 5 or 10, which is very important and was advocated strongly by Dr. Ostland. But Dr. Egerton suggested to the veterinarian here that why not give some of this new stuff to the mouse? And needless to say, you'll know what's coming next. It's this, the little glove. So it turns out that it's active not only against many roundworms or nematodes, but against many insect parasites, such as fleas and lice and so on, and acarines, the various mites, very potent against those. So it set a sort of new standard. People keep talking about revolutions. Well, this really was a revolution in veterinary medicine and animal health because you had a drug now that was extremely potent, many formulations. You can just pour a little along the back of a cow and it'll kill its parasites inside and out. It is just a whole new era, and it has caused problems now because everybody else is trying to match that, and one of the eminent professors at McGill University recently said, you know, this is a mistake. We ought to try and get better ones without necessarily being as good as, but just something different because of the threat of drug resistance, which is ever present. Now, I'm going to come to river blindness, which is the part of ivermectin application that in a way is of perhaps most general interest. And river blindness is the disease onchocerciasis because it's caused by the worm called Onchocerca volvulus. And you will see in a moment why river blindness is pretty misleading, but also you can understand why it's called that because that is the most important single aspect of it. And this sort of scene you see here with a blind adult being led by a child is sort of one of the icons of this whole disease. And it occurs as an extremely oversimplified diagram, but it shows you that it occurs in Central America and the northern part of South America, a bit more than indicated here, and across the equatorial belt of Africa, but of course not uniformly. And I'm going to show the next slide rather quickly because my intent is just to give you an impression of the disease rather than go into a discussion of the disease itself. But the things that are important to know is it's transmitted by a small black fly. In Africa, it's usually Simulium damnosum. And the fly brings the infection, it bites somebody, deposits the microscopic infective larvae on the skin, and those larvae burrow under the skin using the bite site and grow up to be big worms and to give live birth to progeny, microscopic larvae called microfilariae. And they grow up in that nodule capsule formed by the host, and when they it's vascularized, and they give birth to this progeny, thousands of them every day, and they spread then through the skin itself. So here is a diagram showing the microscopic larvae escaping from this nodule and migrating all over the skin. And of course, you'll see one there indicated where it reaches the eye, and of course, where the problem of blindness comes in. And if the nodule happens to be on the head, which is very likely, especially in places like Guatemala and in Central America in general, then, of course, it's even more likely that some of those migrating larvae will reach the eye and cause damage in the eye. What happens with those nodules is that they are of cosmetic concern. They are not painful. They're not tender to the touch. But you see in the little inset up in the right-hand corner, if you opened one of these, you would see the worms inside. It'd be sort of like a walnut shell full of angel hair spaghetti, that sort of thing. These long worms entwined inside this nodule from which the larvae escape. And you see a cross-section of microfilaria in the skin, just showing how deep it is. And the little boy on the right has had the infection for maybe half a year because now the nodules have adult worms who are releasing these larvae, migrating through the skin, causing this tremendously itchy maculopapular rash. And you can see the striations on his body where he's been scratching himself. And this is a really extreme itch. And the bite of the black flies, incidentally, is also really bad. And these people get, in endemic areas, get huge numbers of bites. So this is the sort of the first stage, although it doesn't happen until about half a year, the rash comes. And then you have various conditions of skin damage over years, because these worms live 15, 18 years maybe. And every day, the females are releasing thousands and thousands of microfilariae into the skin, and they're migrating not under the skin, but sort of in the skin, as you can see. Now, the upper left-hand picture there shows one of the things that happens as the skin loses its elasticity. And And this is a condition called presbydermia, a word that will be readily understood by Presbyterians because, of course, it refers to a young person having the appearance of an elder, a tough-skinned elder. So that's one of the things that happened. And down in the central there, you have a village elder. And a man I saw in West Africa years ago, and he had long gone on, but when he raised the hem of his garment, you could see that he had that, what you see on the right-hand side, which is called leopard skin, very characteristic of this disease. It's a very abrupt pigmentation, more abrupt than, say, with leprosy. It's a very characteristic thing. It can be used in epidemiological surveys. And also they have a formula worked out that if you have a village has so many of these, then it will have so many other infected people that haven't got to that stage. And the same sort of thing is done with nodules. You use formulae to try and establish a village level of disease, level of disease. The big problem, of course, is when these invade the eye. And it can do damage in the anterior chamber and in the posterior chamber. On the left, you'll see the cornea being damaged with these things that are not very clear, but they're little white patches there. They're called fluffy opacities or snowflake lesions. And those are caused by the invasion of these larvae. And we now know, at the risk of saying more about this than I intended to, that the damage is not actually caused by these microscopic worms living there, but dying there and releasing bacteria that infect the worms. So the people have worms and the worms have bacteria. All of them have bacteria. And as years go by, also you get this sclerosing keratitis sort of coming up from the bottom of the eye. The cornea becomes more opaque, and eventually the whole cornea becomes opaque, and the person is blind, such as that man in Togo that I took this picture of years ago, totally blind. And they're hoping for treatment, but once you're totally blind, ivermectin isn't going to help. And it's a tragedy on many levels, because it's a particularly important disease near rivers, and because that's where the black flies breed. And if there's a lot of disease, the villages become abandoned. And this village had obviously been pretty prosperous, to judge by the building construction. So those people move away from the rivers into less fertile land. And that in itself is a tragedy, that they're now trying to exist on much inferior land. And of course, it's a tragedy in the individual level and in the community level, because people cannot work. And it's also a tragedy because they cannot work and the children cannot go to school because they are taking care of the adults and trying to help them do some work in tilling fields. There was a very ambitious and wonderful attempt to control the disease by controlling the black fly vector, by spraying insecticides on fast-flowing rivers, because that's where they breed. Spraying things in fast-flowing rivers has got all kinds of problems, as you can imagine. This was a wonderful program, though, and for me to be there and see helicopters and fixed-wing aircraft and cars with the name Onco on it was a great thrill in itself. You don't normally see aircraft with the name of a worm on it. And this was funded by WHO, as you might be able to make out there. A very ambitious program, but totally unsustainable in the long run, but being operated in a marvelously efficient way, but the odds tremendously against it. So the question then is whether or not chemotherapy would be beneficial. The man on the left is blind, as you can see. He's being led by a young child. Not in this picture is an older brother whose eyes are already infected and they're watering. And it would be nice to have a drug that would kill both the adults and the nodules and the microfilariae in the skin and in the eye. Ivermectin does not do that. It kills the microfilariae in the eye. There had been a previous drug that did that, but it was extremely dangerous to work with. So the initial studies in people had to be done extremely cautiously. But it turns out that it does kill them in a very safe way at a very small dose. And it does affect the adults. Although it doesn't kill them, it does reduce their capacity to produce these larvae. And therefore that adds to its ability to prevent disease. So what happens then is that this drug, if given prophylactically once a year, will prevent the skin lesions and the blindness that ensues. And I had a chance in the very early clinical trials to go to Togo in West Africa, south of the Sahara. And just a couple of pictures, going to those very remote villages to treat villages at a time. And it was great at that time, great controls and record keeping and so on. Everybody was weighed on the bathroom scale and got their drink. The picture, the more colorful one on the right, is a recent picture because things have progressed and become more efficient. And instead of getting on a bathroom scale, all you need now is a pole that has been marked as to whether you get 1 pill or 2 pills or 3 pills, and it works very well. Now, I should say that I have always had great respect for worms, having devoted my life to them. I've never felt any conflict between the fact, on the one hand, that I really, really like worms, and on the other hand, I spent most of my life trying to kill them. But I mean, I admire them. They are absolutely marvelous creatures. And most of the paintings I've painted have been about worms on my half hours. Most of the poems I've written have been about worms. And one of them happens to be about Onchocerca. And, you know, the idea is to sort of give some thought about what, from their point of view. And so Onchocerca speaks. Onchocerca, I don't need your goddamn eye. All I need is a bit of skin big enough for me to scatter a few larvae in. Just enough to make it probable that there'll be a pickup and delivery. Don't look at me that way. I don't need your goddamn eye. Now, I should apologize for the language, but worms are like that. Now, just a brief mention of another disease, very briefly, because there is a related disease, filarial disease, that causes a lymphatic filariasis, and a certain subset of those patients will go on to elephantiasis with the sort of horrendous picture you see there, but more common, the one you see on the left, this lymphedema. Ivermectin is being used in a big control program now designed to actually eliminate this disease, and I just want to mention that because it's important in its own right, but it's not what I'm talking about. I also want to make a big point of the role of this in animal health and veterinary medicine, because people often aren't aware of the impact of parasites in their everyday lives. But the reality is that the cost of our chicken dinner, the cost of our beefsteak, the softness of our wool sweater, the durability of our shoes, all these things depend on the efficiency with which their parasitic diseases are controlled. And in some cases, it depends almost entirely on that. But in all cases, it is a factor. So it's a very, very important factor. And it's not just then important in veterinary medicine and animal health, but it's important to humans because the vast proportion of the human population eats meat or wants to eat meat and wears clothes. And the production of food and fiber is important not only to veterinarians and farmers, but to people. So I think, and of course in this case, highly profitable for the people who make it and develop it and enables them to do other things. I'm going to mention the dogs one, which happens to be also important in its own right and for different reasons. But also this happens to be my own little bit of bench research. I happened to spend some time when I got back to the bench. I happened to have set up a heartworm program entirely unrelated to this. Just before this happened, this drug, and so I was all set and ready to check this drug tested in heartworm disease in dogs. And it works, and it led to once-a-month treatment to prevent heartworm disease in dogs instead of the prior daily treatment with a different drug. So the question then is, what do you do with a drug for onco? The people who need treatment don't have money to pay for treatment. And the little boy over on the right there, that's not his cell phone he's holding, that's the end of the pole that he's holding. So these are people who are in no position to pay for this. Am I doing all right for time? I guess I'd better. I'm almost finished. So what do you do? Well, we, of course, would have liked to have sold it at vast profit, but obviously that was not in the cards. We would have liked to have given it away to an aid agency at cost price, and then they could use it and so on, but that was totally out of the question. So in the end, there was nothing to do but to give it away. And that turned out to be, it was very difficult. It turned out to be extremely difficult to give away a drug for a variety of reasons. And it resulted in the creation of a whole different infrastructure for medical delivery of different organizations. Merck set up a program down in Atlanta, Georgia, with top medical experts to control and make sure that this happens. It's a very, very difficult thing, a very complex operation. So there are many, many organizations involved, many NGOs, non-governmental organizations, World Health Organization tremendously involved, the Jimmy Carter Center in Atlanta, Georgia. And here you see a poster advertising it, and you also see that it is a little pill. And it's very fortunate, really, that it can be given by mouth. It's a tiny little pill. The most anybody would ever need would be 3 of them, and you only have to give it once a year. I mean, it worked out much better than anybody had any right to hope. Now, this is my shamelessly self-centered aside. I apologize for that. But I have an excuse. This is my wife, Mary, and I at the United Nations, obviously taken some time ago. But my excuse for showing this is the 2 guys on the right. The first one of that pair is Roy Vagelos, the chairman and CEO of Merck, who was a physician and a top research scientist. And it was his call in the end to whether or not to give the drug away. And so he made the call and made the announcement, then realized he really should have checked with the board of directors first. But it all worked out in the end. And then the far right, there's somebody I don't know if you know in this country or not, Jimmy Carter, former president, who's tremendously involved in this. He knows a lot about it. He may not get everything right in terms of the life cycle of the parasite, but he certainly knows them more than any other ex-president. So the result is that this drug has been given away in increasing amounts over the year. It's now been going on for 25 years, and this is the number of treatments, not the number of people, because some of these people, for example, in the middle there somewhere, there might be, say, 60 million people and 60 million treatments in 1 year. Some of those people would have had an annual treatment every year for maybe, say, the last 5 years. Others would be getting it for the first time, so you can't really add the numbers of people. But it's now up to the incredible numbers of a billion, more than 1 billion treatments given away in this space of time. And these boys that I saw in Togo so many years ago, if they remained in the program, should now be in midlife and should be free of skin disease, which as a teenager, of course, that's what they worried most about, its effect on marriageability and so on. But so they should be free of skin disease, and they should be free of blindness. And so scenes such as this sort of iconic picture, scenes such as this, just as the individuals themselves in the picture are receding, and if all goes well, should eventually be gone. Thank you.
thank you, Bill, for a very inspiring lecture. Thank you very much. We can now have time for questions.